So far, we've explored some interesting techniques in deep learning to perform object classification, object detection, and even image segmentation. A common characteristic with all of these techniques has been the need for large amounts of training data to let the machine learn a model that is sufficiently generalizable so that we can apply these learnings to new, previously unseen data. In this lesson, we are going to explore how we can use transfer learning to boost the performance of problems where we have a limited amount of training data. Transfer learning is a technique where a model developed for one task is reused as the starting point for a model to be trained for a second task. It is used to speed up training. Think of it like jump-starting the entire process, and to improve the accuracy of your deep learning model.
The process of training a deep network is often expensive. It is expensive in terms of time and also in money to source the sample images and then to label them. Complicated labeling, such as the creation of semantic segmentation masks, can be even worse. On top of this, the problem is compounded by the fact that deep networks, such as CNNs, are data hungry. The more data, the better usually. Can we somehow use an existing classifier as a starting point for either a slightly different or a new task? It turns out that yes, we can in many cases. What we have described here is the concept of transfer learning, where we are improving the learning in a new task through the transfer of knowledge from a related task that we have already learned. You can think of it like learning a slightly new skill, but one where your previous experience has helped you. If you want to train for a similar task, but a new class of object, this is the type of transfer learning often referred to as pre-training. And if we want to train for a slightly different task, but pre-initialize using an existing network model, then this is typically just called transfer learning. As concrete examples, if we've learned about visual object recognition, and we want to learn to recognize a new category of object, we can assume that our original classifier has learned lots of useful stuff related to detecting and recognizing objects. For example, its CNN feature extractor has probably learned about edges and gradients, object saliency, and region proposals. These concepts that it has learned should lend themselves well to the detection of a new class of object. Additionally, if we want to take our existing object detector and extend it to perform fully convolutional semantic segmentation, for instance, depending on our network model, we can treat this as transfer learning. We've learned a new skill, segmentation, based on our learnings for our previous skill or skills. In this case, object classification and detection. We're making assumptions about the training data used to train the original classifier, the base network. It must be of a relatively similar domain to that of the new task, and the features we've learned previously must be relatively applicable. There must be some relationship between the knowledge behind both of the learners. The implications of transfer learning are pretty significant. First, it potentially significantly reduces the amount of new training data required, and that has huge practical consequences, such as savings in both cost and time. In many cases, the volume of data needed otherwise might simply not have been available to train on. Pre-existing datasets can be used to precede the training for the new model. This can lead to faster training and faster convergence, and often more accurate results. Secondly, it allows training from simulation. For instance, many real examples of autonomous driving systems are initially trained using 3D simulations of roads, pedestrians, buildings, and the environment. An important consideration for transfer learning, where we're using pre-trained weights, is whether to allow fine-tuning of these weights or to freeze them entirely. If the target dataset is significantly smaller in size, but of similar content to the original dataset, it is not always a good idea to fine-tune, as it may lead to overfitting. Since the data is similar to the original data, already learned features are very likely to be relevant, transferable, to this new dataset as well, and are already generalized in form from the content in the larger original dataset. If the target dataset is relatively large in size, and again of similar content to the original dataset, we can try fine-tuning only, as we are less likely to overfit. If our target dataset is smaller in size, but quite dissimilar in content to the original dataset, it is becoming increasingly more likely that the later domain-specific layers in the original network will have learned features that are not relevant to our target network. In this case, it might work better to remove some of these later layers and add any new domain-specific layers to activations from earlier in the network. If our target dataset is large and dissimilar in content to the original dataset, we could train from scratch. But in practice, it is often useful to initialize with weights taken from a pre-trained base network model. However, we don't need to freeze any of the layers, and we would typically just use our original weights as a starting point. Additionally, we will tend to transition from having general, well-transferable features early in the network to more specific, less transferable features in later layers in the network. This is called domain discrepancy. More advanced strategies might take account of this and could include using different learning weights by layer. That is, adjusting the learning weight of a layer, determining how slushy to make it from fully frozen to fully tweakable, depending on that layer's depth within the network. In an upcoming lab, we'll see an actual example of transfer learning where we take a ResNet object classifier network and extend it to perform semantic segmentation. We'll first modify the network by adding additional convolutional layers to perform the segmentation. Next, we'll take the pre-trained weights for our initial network and use them as a seed for our segmenter. We'll experiment with both freezing these initial weights entirely, and thus only training the new layers, and with allowing that initial preceding of weights to be fine-tuned and optimized in conjunction with the new layers.
In this lesson, we discussed transfer learning and how we can use it to reduce training time and improve performance. One of the well-known challenges in building a supervised deep learning system is sourcing a sufficient quantity of labeled training data. This is often a very time-consuming and resource-intensive task. Thankfully, transfer learning is a powerful means by which we can often reduce the amount of application domain specific data that we'll need at the onset of our work.